And so the answer is we can take a nominal level measure and we can convert it in a way that would allow us to use it with this kinds of statistics that we're going to talk about in this class. The most common way of doing that is dummy coding, and so I just want to talk a little bit about that. And dummy coding is something that you'll have to do with the data that you're working with for sure. And what we do is we generate a number of variables such that in any given column, membership in a given category is coded as 1, whereas non-membership is coded as 0. And the number of coded variables needed is k minus 1, where k is the number of different groups in the nominal measure. So if we have red, green, blue, k is 3. So we need two vectors. We need 2 columns of data in order to represent that. And so the somewhat rhetorical question is, why is it k minus 1? Why isn't it k? It's k minus 1.
Because we are comparing the term we are dropping with the other.
What's that?
The level we are dropping is the one we are comparing the others to.
It is. It is. I'm not quite sure that is. I don't think that's exactly how true. That might not, but I don't think that's the clearest answer. The clearest answer, I think, is because with k minus 1 columns of data, we can perfectly represent k categories. We only need k minus 1. And when I say a vector, I'm talking, it's a column of data, right? So think about a data set and a vector. Sometimes I say column, sometimes I say vector, but it's a column, a single column of data. So we can perfectly represent k categories with k minus 1 vectors of data. And let me show you. Next slide. Can't see this very well here. You can hopefully see it well in front of you. But I have this data set that I have this variable called favorite color, nominal, right? And then I dummy coded 3 vectors of data, which is 1 more vector than we need. And we can see that if we have any 2 of these 3, we know what the third one is, right? If it's not red, or if it is red and it is blue, then it has to be, everything else is green, right? And so with any 2 of these, or if we had red and green, we know if it's 0 on both of those, then it has to be blue. And so, and in fact, if you try to put all 3 of these into, for example, a regression analysis, it will remove one of them, because it'll say that this information is redundant. The correlation is too high, and we'll talk about this when we talk about regression. To dummy code data, we just think about needing k minus 1, k being the number of, in this case, 3, red, green, blue. If the data you're working with has 8 different groups, then it's going to be 8 minus 1. You'll have to generate 7 different columns of data. And I'll show you here in a few minutes how to do that in SPSS. Play around with the menus long enough, and you'll be able to figure that out yourself. But I'll show you how you can easily do that in SPSS. So that's nominal, and then the next level of measurement, and so we're sort of moving up. Nominal, we have the least amount of information. Ordinal, the way that I think of ordinal is we have some order, right? Nominal is all we have as a name, in name only. Ordinal, think of the word order, we have some order there, right? And so ordinal reflects the magnitude or the amount of some quantity being observed. The numbers indicate some position in a sequence. Intervals between the numbers are not equal though. If we were to do a public opinion poll and have people rank, or if we were to rank order the most important issues, that rank order would be ordinal in terms of its level of measurement. Because while 1 is the most important, the difference between 1 and 2 might in all likelihood wouldn't be the same as the difference between 2 and 3 and 5 and 6. And so all we have is some order. If we were all to run a marathon and we just captured the order that we came in, not the time, just the order that we came in from the person who finished first to the person who finished last, that ranking would reflect an ordinal level measure. Make sense? So nominal, in name only, ordinal, looks like the word order. We have some order. Interval, intervals between adjacent scale values are equal with respect to the attribute being measured, but the 0 is arbitrary, right? 0 doesn't mean absence of the thing that we're measuring. I don't give an example here, but what's the example that gets used most often when we talk about interval level measure? What's a good example?
Age.
So that's sort of a philosophical thing, isn't it? Can we be 0? Can we be 0? Right. So that's the question. I think we can be age equals 0. But you might disagree with me, and it would be utterly worthless for us to have that debate here. But so I'm not sure that age is the best. But I think age to me is more ratio, because again, philosophically, I guess you can be 0, and we're not going to do. What would be another example, or what would be? Yeah. So temperature measured in Fahrenheit and Celsius is probably the example that gets used most frequently, right? Because the difference between, let's just talk Fahrenheit, difference between 80 and 81, that 1 degree, it's the same anywhere along that scale. But 0 Fahrenheit does not mean absence of temperature, right? Zero is arbitrary. 0 Celsius doesn't mean absence of temperature. I don't know that we'd say that it's arbitrary, but it's at a point that is meaningful. So most frequently, if you pick up an undergraduate stats book or undergraduate methods book, it's going to talk about interval level measure, and it's going to say something about temperature in Fahrenheit or Celsius, because that's really the example that gets used most frequently. The statistics that we'll talk about in this class, so even some basic things like Pearson's correlation coefficient or regression or ANOVA, some of those t-tests, some of the statistical tests that you may have seen, the dependent variable for all of those has to be interval level data. That's a prerequisite. If we look at what are the requirements to do we'll look at this. What are the data assumptions for doing multiple regression? One of the assumptions is that the dependent variable is measured at an interval or ratio level, not ordinal. And so it sort of leads to this somewhat confusing, probably at best, problematic. Some people might say, or concerning. Some people might say, at worst, practice that we oftentimes see in the social sciences, that we have a Likert or Likert type scale or a semantic differential scale, and we treat that as if it were interval level data. And does everyone agree that it meets the assumptions of an interval level measure? If we have something like this, where I'm asking about the current president for another couple of days, and I'm asking people to give me some impressions of that, and people circle somewhere between selfish and unselfish, where they think where their perceptions lie. Is that the same as temperature? Why not?
It's up for people's interpretation. And so, people could, 2 to somebody could be way different, between 2 people.
Well, a 2 for you might be a 7 for me, or vice versa, right? And so those numbers 1 through 7, there's some interpretation that happens in our head as we put numbers down, or as we circle or check or do whatever we need to do, right? And that interpretation isn't always the same. So it is clearly different than me sticking a thermometer in a thing of water, and a digital thermometer, and pull it out and it says 98.7. And then I do it again and it comes out and it says 68.3. I can have some confidence that those measures, the difference between those 2 measures would be the same as the difference between any other 2 measures that we're going to do with that Fahrenheit scale. And so the dirty little secret, really not, but the concerning practice that, and I've been on some dissertation committees where people from outside of communication will bring this up, where the researcher has something that was collected in like a semantic differential scale, like we just saw on the previous screen. They use that kind of scale, but then they treat it as if it were an interval level measure. They use statistics that the assumption is that it is interval level data. And so that's a violation of that assumption. If the assumption is that for regression that your dependent variable is interval or ratio, and we're using something that isn't, then we violated that assumption. What's the argument that you could make to sort of counter that? If somebody says, well, you need to use some other procedure that has the assumption of ordinal at level measure, because I think for sure we probably would say that this is at least ordinal, right? I think we could probably say that this is at least. No, we could go down that rabbit hole if we want to, but I think we probably would say, most of us would agree that this is at least ordinal. The question is it interval? So they might tell you that you should use some statistical procedure that the assumption is that the dependent variable is ordinal. But what would your argument potentially be? What would you say to some person from political science or sociology or the outside member who?
It's absolutely true. I think that if somebody was to pick a 2 on the selfish, closer to selfish, and somebody else picked a 6 they're probably each thinking different things. But the argument still remains that the difference between the 1 and the 2, the difference between the intervals, would still qualify. And then if I have a really big data set, maybe somewhere those differences get
I like that.
sort of
Yeah, that's it
adjusted
exactly.
out.
Yeah.
And so I'm making a case for myself to use it.
Yeah, and if I were on your committee, I'd say, great, okay, thanks, that's good, let's move on. And that's the answer that, it's the idea that, and it's the idea, we don't know that this is necessarily true, it's the idea that whatever errors there might be could cancel out over a large enough set of data. Where if I'm sort of on the way that I think about something is more extreme on the high side and somebody else is thinking about it more extreme on the low side, those things with a large enough set of data has the potential to cancel each other out. And there's no strong reason to believe that that randomness, which I think we call it that randomness wouldn't, with most data that we collect. There might be some data collection. Maybe you're working with a group of highly charged partisans and you're doing something about politics. That argument might not work quite as well there. So but that would be essentially the argument that errors will cancel each other out. Therefore, we can use our semantic differential or Likert scale as an interval level measure. And so, and I'm comfortable in this class with you doing that. I do that. I don't know of anybody in the department that doesn't do that, but it is something that will come up potentially, either when you send something out for publication or when you're talking to colleagues that are doing work. So we have nominal, ordinal, interval, and then ratio, right? And the difference here is that same thing as interval. It's just that 0 means absence of whatever it is that you're measuring. So 0 means it's not there. There's none of it. It's 0. It's not arbitrary. It is the absence of whatever it is that's being measured. An example there might be an example of a ratio scale.
Temperature in Kelvin.
What's that?
Temperature in Kelvin, height, weight.
Right. Temperature in Kelvin would be 1. 0 means absence of molecular motion or whatever. I'm not. That isn't really at mine. But height, weight. Yeah. GPA. Huh? There's a 0. What is it? Is it? So there's not a right answer to this one, I don't think. People can think differently about it. So GPA, interval or ratio?
I'd say ratio because I mean you have it's like
You got all F's, right? You got 0, right?
Yeah, it's like if you put it like a sports game, you score points, but you have 0 points.
That's the interval because 0 actually means something else. Because 0 means you scored F in every class. So 0
Yeah, it's not
actually
the absence
means
of
0.
Would it depend on how you're using that particular variable, right? If you're like using it as a measure of knowledge, right, then GPA isn't a
Or performance in college.
yeah, right.
If GPA is a measure of your performance at the college level, I got a 0 GPA. Boy, I was bad. It wasn't good, right? But does that mean I have absence of performance? I don't know. It means something. So I think, but yeah. So I like that point.
Absolute accomplishment.
What's that?
If you're measuring accomplishment, that's an absolute 0. So you accomplish literally nothing.
I turned that paper in. I came to class once. Yeah. What was your example when you? What was the example where you the first? So
Well, Yeah, I'm just making a
Yeah.
devil's advocate argument.
Yeah, no,
for
I'm
the
glad.
ratio.
Yeah.
You know, like,
Yeah.
you know, if you don't score in a game, that's a shutout. You were shut out in terms of points you earned through grades.
Absence of. So if we're baseball score of baseball game would be ratio. That's the absence of any points. Yeah, and so I think the argument can be made either way. It's an example that for undergraduates I probably don't. How about GRE? Would that be another one? The graduate record exam that you took. You guys have to do the GRE. Can you get a 0 on that thing?
No.
No,
Mathematically impossible.
I think the minimum is like 400 or so.
Oh, that's a. How about ACT? I think you get a 0 on the ACT, right?
I'm not good.
If you get everything wrong, what do you get, like a 3 or? But I guess they probably all fall into a similar as GPA, right?
Well, the thing about that one is they score you on the percentage of the population, so you can never score below like 0.01% of the population. So it score you like a 0.01, which would give you like a 1.
Yeah. So it just approaches 0.
Right.
You never actually have.
You can actually
Yeah, it doesn't bode well. Assuming you did your best at it.
There is a specific
What about something that has an absolute 0 but the interval doesn't work? For instance, how likely are you to recommend this product to your friends from always to, or from never to always? Like never is an absolute 0. I'm never going to do this, right? It serves as a real absolute 0 in that case. But the interval between your points is, right? We're going to have to treat that like interval, but is there another weird category
Well, I don't know that there's another weird one that would capture that point, but this nominal ordinal interval ratio isn't the only way to think about levels of measurement. Some levels of measurement collapse. It's really with ordinal interval where you have some differences. This is the most common, but there are other ones. But I don't think, so let's think about this. How likely are you to recommend a product? 0 means not happening. Absence of the likelihood is 0. And then you could have some scale that somewhat likely, somewhat unlikely,
could be a
somewhere in the
percentage,
middle.
whatever, something.
Right, yeah. Yeah, that would be sort of a hybrid of a couple of these measures, but I think you'd probably, the safe thing would be to default to the sort of lowest level. And so in that case, it probably, given the other discussion we had, probably you'd use it as interval, right? Instead of you. And from a statistical perspective, whether it's interval or ratio, we can do all of the same things. It's really that difference between ordinal. Once we get to interval, we're golden. But but before that, there's a limited set of non-parametric statistics that you can pull from, and it's limited, somewhat limited. And then, but after you get interval, whether you get ratio or not, doesn't allow you to do anything differently. So in that case, we probably, but somebody might argue that that's ordinal, right? Even though you have a 0, that for the same reason that they would argue that the semantic differential that I had up here. So so good, and so hopefully that, I don't know, does that clarify more than it confuses? I was going to say hopefully that clarifies more than it confuses, but I don't know if it did or not. But I think it's one of those things that I think it's useful to think about. It's useful to think about. There's just so few absolutes, and when we start talking about, there's just, I hope I never use the word never. But and so that's circular, right? And so, but there's always exceptions. There's always ambiguity. There's the researcher has to make the argument for the steps that they took. And if said researcher can make a convincing argument to a set of reviewers and they give you the green light, you get it published, and then it becomes knowledge. But that doesn't mean that others couldn't quibble with that, or if you had different reviewers, that they might have told you, no, this doesn't rise to the level of publication. And so we're sort of always dealing, in this class, we'll always be dealing with those kinds of things. And I might tell you, well, you just need to make an argument. You can do it that way, or you could do it this way. Decide what makes the most sense for you. Make the argument for why you did that, like the argument that was given a few minutes ago for why we can treat this Likert scale or semantic differential scale as an interval level measure. Make that kind of argument and just see what happens. It's the marketplace of ideas, right? And see what works and see what doesn't work with the audience that you're working with. So far, so good. Another sort of key concept that might have been a part of a previous class that you took, but clearly will play a role as we move forward in this class is this idea of measurement error. And measurement error is the degree to which the observed values are not representative of some true value, right? And in most cases, we don't know what the true value is, or we would have just used that. And so in most cases, we don't have that true value. We're trying to get at that. And one way to sort of conceptually think about, and it dates back to the early 20th century, and if you pick up a statistics book, you'll see people still talking about classical test theory, is that we have some observation that we make, and that is our X. So that's some data that's collected, and that theoretically, although not practically, theoretically we can decompose, we can break that observed data into a true part of the measurement, the true score, and then some error component. Obviously, all we have is X. We don't know what part of that is true and what part of that is error, but conceptually we can think of measures as being made up of, we have X, and X is made up of some true score, we hope, and some error that is collected as part of that. Can we measure anything without error? If we measure age, can we get that without error? Weight, can we get that without error? Why are you shaking your head? Weight.
Because I'm just thinking, like, even age, for example, like, if I was to say somebody's 23 years, it might be 23 years and like a couple of hours. So
Right.
the hours factor.
Right. Yeah, and if we're doing self-report, you might just mess with me because you're the kind of person that likes to mess with me, and you're really 23 and you say you're 19, right? Or whatever, right? And so I think regardless of what it is that we're measuring, there's always going to be some imperfection. Somebody think of an example where that might be less likely to be the case.
Well, I think with weight, it may be like if you were to measure on scale, for instance, it'd be less likely, but still every mechanical instrument has some measure of error.
Right. It only goes to hundredths of a pound, and we could take it to thousandths of pounds, or we only got to milliseconds, and maybe we need something more fine grained. And so, so there's no, especially with self-reported data, there's going to be, even with the ask students their age, or ask them whether they're, ask them their gender and have them report that. They're just, I don't know that you can measure without some error. Somebody think of an example. You guys are smart. what would prove that wrong? Homework for next week. Think about something that, oh, we could for sure measure this. Maybe computers can measure. Maybe computers. But even there'd be limitations on what it can do.
Number of people in the room.
What's that?
The number of people in the room.
Yeah, so we could count if I were going, but so let's say my job was to go out and count the number of people in rooms. That's what I did for a living. I might get that right most of the time, right? We'd hope, but could I get it wrong sometimes? So there would be, I could, especially a large auditorium where there's 60 people, it might just be when you get towards the back. So potentially even something as straightforward as, of course we could count the number of people in this room, and I think we'd mostly get it. But if we had to replicate that, do that as a form of measurement over and over, I think then it might become more likely that there'd be error introduced.
I was also just wondering, can we calculate without error? Because I was just thinking, algebra or calculus, sometimes they put the plus e and those are methods to really get it to sometimes the 100 points of no error,
But then the next person could come by and say, well, you only did it to 100 decimal places. We need it for this thing to 1,000. And if we got it out to 1,000 decimal places, again, this is the extreme, right? And not the practical, but it's the extreme. There might be some things that, for all practical purposes, we can measure those kinds of things. Weight, I think, would be time in milliseconds for our purposes, probably. But even something as simple as, I don't know, do you guys still have a computer lab downstairs? There used to be a computer lab downstairs where faculty could use it for research and graduate students. Is that still there? Well, when I was here, I'm sure you guys have done a lot since I left. There were I think somebody donated. I think IT said, we have some computers that we're either going to throw in the trash, or you guys can use them in your lab. And we took them for our lab. And there were Windows machines, and you turn the machine on, and it's got to think about the antivirus for a bit, and do I need to update that, and does Windows need an update? And the best practice was going there the night before and turn all the machines on, and then come back the next morning and hope they're all still running, and they've done all of the things that they needed to. But even if we're measuring latency in milliseconds, which is what we did, when they pressed the keyboard, the spacebar on the keyboard, it would capture some response in milliseconds. Well, if the CPU is busy trying to update the Norton antivirus or whatever it was doing, that could just add, and it was doing it on some of the machines and not other machines, that error, that noise that would be introduced would potentially be problematic, and not random error. It would be error that might be systematic in a way that's problematic. So I think I probably beat that idea to death. This is just if we wanted to represent that in terms of variability. Formula is the same. We have X, which is the variability that we captured, and then we have T, which is the true variability, which we don't know, and plus or minus some error variance, again, that we don't know. And we can think about the error term and think about what some of those errors might be. It might be a conceptual error where we use some proxy instead of the variable of interest. We think you wouldn't do this purposefully, but maybe you think counting the number of books that somebody has on their bookshelf at home is a good indicator of socioeconomic status, which some people do. Whether it is or not, I know that measurement, socioeconomic status, well enough to know whether it is, but it may not be, right? And so if conceptually I don't have many books on my bookshelf, but I have a Kindle that is full of books, and probably buy a new book every week, and for the most part I get through most of those books that I can handle. Some are fiction, some are nonfiction. But if you ask me how many books I have on a bookshelf at home, I guess I have a couple, but that's it, right? And so that would be so it could be conceptually we're not actually getting socioeconomic status. We're using some proxy to get at that. That is problematic. We probably don't know the size of the error. It's unknown or which direction. If we did, we probably would make the changes, right? And so it's a serious and probably, as I say here, the most serious type of error. You want to measure socioeconomic status. You say you're measuring socioeconomic status, but your proxy is getting something else. And obviously that error, in that case, the E is going to be has the potential to be quite large. So that is one type of error. Another type of error would be these systematic errors. In this case, do I use the term there? What do we call this? There's a term that we use. I don't see it. What do we call this kind of error? Huh? This when people provide erroneous answers to income, whether you smoke marijuana on a regular basis, whether you voted in the last election. There's a
Social desirable.
yeah. So it's socially undesirable to say your income is $8,000 a year, right? And so people might, and it's socially, like it or not, socially desirable to inflate that, right? And likewise, are people more likely to, if you ask your undergraduates whether they smoked marijuana in the last, let's say month, to give them a little bit of, what are they likely, what error are they likely to give you?
Depends on what state they're
What's that?
from. Depends what state they're from.
Right, it could be Colorado or Washington or some of those states, but save that. Are they more likely to tell you? Are some kids going to tell you that they smoked marijuana in the last week when in fact they haven't? That's some might, right? But maybe it's a cool thing to or maybe it's not crystal meth, right? Maybe that's, I don't know if that's cooler than marijuana, but it doesn't seem, as much as I know, it doesn't seem to be. And so we could ask about that, and there's probably the coolness would fade pretty quickly. And so ask them the last time they used crystal meth, and there's probably not going to be many kids that say, yeah, I used that last week, when in fact they didn't, right? Most of them are going to be, and they might not be your students here, right? This might be a difference, right? Where they're a habitual user, and they tell you that they're not, or they've used it in some period of time, right? So it's socially undesirable to, I guess it's socially undesirable to, in some circles, to say you smoke marijuana, in some circles to say you use crystal meth, and so that's the and voter turnout. What would people tell you that they? Yeah, you wouldn't get many people who did vote who said, no, I didn't vote, right? Some, right? There'd be some people, just to play with you, just to mess up your little survey thing, right? But most of them would be they didn't vote because it's socially undesirable to say that I didn't participate. There'd be pressure, right? And so it's a systematic error, right? We know when we collect voter turnout data, 80% of the population tells us they vote. And we know that it's just a little bit over, it's just north of 50%, right? And so there's a lot of, but it's biased in a system. It's systematic error, right? It's biased in the case of the voter turnout data. It's biased on the upward side. We could have another good example. As much as I love Burton, I've collected data. I don't know about this room, but some of the other rooms down the hall. You guys don't know exactly what I'm talking about. And you collect data on one of those days when the radiators are doing their magic, right? The banging noise, right? Everybody know the banging noise. And maybe that's what they're fixing here. Who knows? But the banging noise has been around forever. And I've collected data where that noise is just jarring. And then the next group that comes in, or the next day that I collected, or I figure out that if I go mess with the thermostat, it makes it better or worse. And then the next group has a different experience. And that would also, that could also systematically impact your collection. Old computers where you're trying to measure milliseconds, in all likelihood, the measure is going to be systematically biased on the upward side. The presence of systematic errors leads to biased results. The direction, the magnitude of the bias cannot be determined without knowing the direction and magnitude of the errors. In many cases, we do, but we don't know. If we ask people whether they voted or not, what they used to do is they'd actually go to the clerk of courts and say, "Can I see the voting rolls?" Because it's public record, and you can actually, if somebody tells you they voted, you can go to the clerk of courts and you can find out whether they voted or not. Really, really expensive, right? But besides that, you have no way of knowing who in your data might be telling you the truth and who isn't. You know that there's more people that tell you that they voted when in fact they didn't, but you don't know who those people are. So the error tends to be really difficult to work with. And then I think finally, random errors would be just some of the things that we've talked about already, where just a temporary variation, or somebody that might be biased in one direction. There's no good reason to believe that there would be somebody else that would be biased in the same magnitude or at the same magnitude in the other direction. And so those errors, if the sample is large enough, tend to cancel out. And when we talk about measures of internal consistency, this is the kind of error that we're capturing there when we're doing some kind of reliability. Sometimes we call it alpha, and people know that we're looking at convex alpha, and we're just trying to assess, in this case, random errors or that non-systematic error. It's just that temporary fluctuations one way or the other. Just a couple things about convex alpha, and these will be useful when because we don't spend a lot of time talking about this, but you have to use it as we move forward in the semester for some of when we start talking about exploratory factor analysis, or maybe as you put your data together for the homeworks that we do in this class. It measures unidimensional, single-dimensional constructs, and so sometimes we might have speaking apprehension.
Communication apprehension.
What is it?
Communication.
Communication apprehension. It's a multi-dimensional scale, right? What would be the different dimensions of that?
It's public, interpersonal, dyadic, public dyadic, group, and meeting.
What was the last one?
Like business meeting.
Oh, good, yeah. And so, but convex alpha doesn't. It can't assess all four of those dimensions. It could assess any one of those four by itself, or you might think that they're all four correlated strongly enough that you just throw them all in a measure and call it communication apprehension. That includes all four of those dimensions, and that's what convex alpha can assess. The range is, in practical terms, from 0 to 1. But actually, mathematically, it can range from negative infinity to 1. But if you get a convex alpha that's negative, there's some problems with your data. Something needs to be reverse coded. A couple things need to be reverse coded, and so but there's likely some issue like that you need to resolve. And we can think about alpha as being, 1 minus alpha is the amount of noise or error that we have in the data. So if you calculate your alpha and it's 0.8, 20% of the variability can be thought to be noise. If it's 0.5, half of the variability in your data can be thought to be noise. Alpha above 0.8 is generally thought to be good. 0.6, probably a floor. Maybe if you're doing some research in some cutting edge communication area where others have not been, you might be able to get away with something that's slightly lower than that. But again, it's sort of, you'd have to make the argument for why an alpha of 0.55 is a useful measure when nearly half of the variability is just random noise. 45% of the variability is just random noise. And so you'd have to make that argument, and you might be able to convince somebody of that. How about alpha too high, red flag? I report an alpha of 0.999 on my communication apprehension measure. What does that tell you?
There's not a lot of variance in the responses.
Yeah, it's like everybody did 4, 4, 4, 4, or 3, 3, 3, 3, or 2, 2, 2. Right? It doesn't say anything about where the midpoint is, where the central tendency is. What it's saying is that everybody, for the most part, gave you the same. And so, usually worth a question, right? Somebody reports alpha of 0.95. I always like to ask, well, what was the standard deviation? Within the measure, and how much variability did students or whoever your participants are, did they just read all questions the same and give you the same answer? So, convex alpha, any questions?
I was just wondering, so sometimes if you have a very high convex alpha, is it good to sort of also, alongside standard deviation, we can look at our population, maybe because if I have very adult population and I have a 0.95 or a 0.98, and I know that they are probably the population that would have read it, but I still have, that means.
Yeah, that would be, an argument that probably would serve you well to make that yeah, the consistency is really high, suggesting not a lot of variability within, but given our population, we have confidence that this measure is an accurate reflection of their responses. And so it doesn't necessarily mean it's a bad thing. It just might alert you to ask questions or to anticipate questions that reviewers or committee members might have relative to your research. So just a couple things. So when we have measures that are unreliable, it attenuates relationships between two variables, meaning it suppresses, right? Always suppresses. Nearly always suppresses. Sometimes it can fluctuate. It can just be randomness too, right? And so it nearly always attenuates the relationship between two variables. If we have 3 or more variables, the effects of error are less predictable. The literatures that I've read on it, and it's not a literature area that I keep up on readily, but the last time I looked into it, there is some literature, but it really is idiosyncratic to what's your scenario. And then different authors would say different things about how we might understand that. So if you have unreliable measures, a couple remedies potential would be just the way convex alpha works. If you have 3 items, all things being equal, if you add a 4th item, your convex alpha is going to go up. Or if you add a 5th, it's going to go up some more. Or if you add a 6th, it's going to go up some more. So it seems a little disingenuous. Let me just add another question to my data. And that, again, all things being equal, that should increase your alpha. Maybe the question wording, maybe the quality of the measure needs to improve. Maybe the wording is unclear, or the wording is inconsistent, or the way that your respondents are interpreting your questions don't square with the way that you're interpreting or thinking they'll interpret. So you can improve the quality of the measure in some form or fashion potentially, and then that should add some consistency. And then assuming that the level of measurement error isn't horrible, we can use some statistics, structural equation modeling being one, that allows us to actually model the error. And so we can remove that error and understand the relationship with that randomness removed, assuming that the randomness doesn't outweigh the systematic part of the measure. There's some limits in terms of what one might do there. So I keep looking at that watch. We have 10 minutes, right? So let me, and by the way, don't forget to tell me to turn the recorder off before we leave. And so I think typically, by the way, that's my picture from a friend of mine ran the Disney Marathon 2 weeks ago, last week, 2 weeks ago. And so we spent a week in Disney. And so that's a picture that I took of the Magic Kingdom. Magic indeed. This is I think the thing I'll demo is just how would we take, and that's horrible. I need to work on, I can read it just fine on my computer. Why can't you read it? Is there a way for me to increase?
You just shrink the resolution of your
Of the monitor of the laptop. Yeah, so I will I think work on that for next week. And for the most part, I think like when I do, let's say I want to do convex alpha. And I want to calculate alpha for these 4 variables. I just want to look at the output here once. And so we're going to, what we're going to be looking at is, whoops, sorry. What we're going to be looking at what we are going to be looking at is output. Where is the output? So analyze, reliability analysis. Well, that's a little embarrassing. There should be output that we see. Let me try to do something else. Let's say that I want it to, because you can see the menus a little bit better, right? And you'll be able to see it's recording my screen here, not the, well, it's the same screen, but the resolution here is better than sort of the choppy thing that you're looking up there. Let's say we wanted to dummy code that favorite color variable. I just want to see if I can get it to produce some output. And so what we want to do is transform and recode into different variable. Never recode into same variable. Never recode, this is what your mother would tell you, never recode into the same variable because you lose what you originally had. So always recode into different variable. And let's say I wanted to take favorite color, and I put it here. And I know that I want to call this red. And I change that. So now I want to change that. And so now I'm saying take the favorite color and I want you to transform that into red. And then, how many people have done this before? A few of you. And so then I need to tell it what are the old and what are the new values. And so I'm going to say old value equals 1, new value equals, what do you think? I think red is 1, so new value equals 1. If the old value is equal to 1, red is 1 in the data. Huh?
Else 0 or
Right, so it's going to be old value is equal to 1, new value is going to be equal to 1. And then we could have some missing data in our data, so we don't want to just automatically make everything else, including missing data. In this case, we don't have any missing data. So I might say system or missing data is going to be system or missing data. And then all other values are going to be what value? 0. And I add that. And then let's keep our fingers crossed that it produces some output. It gave me the column of data called red, which every red here is represented by a 1 here. But for whatever reason, in my finite wisdom, I have the not produce an output because that's really what we're going to not spend very much time looking at this because we don't need to be here. What we need to do is produce some output, and then that output, the font is much larger, and that's the thing you'll have to see on the screen. And so, but until I get, anybody have any good ideas why the
Behind your data view.
what's that?
I think it's behind your data view. Your data view is not all the way up. So I think it pops up like behind your data view. No, like not like in SPSS.
So here, right?
Yeah. See, it keeps like flashing behind it.
Does it? I wonder if it has something to do with the recorder. I don't know why. But if